As you begin organic chemistry, it's really important that you know some of these foundational things that we covered in general chemistry, but I just want to make sure that everybody understands these things before we, embark on a journey that is quite extensive. Now, I want you to know I absolutely love organic chemistry, and I hope that by the end of this, you will as well. So let's get started. The first thing you need to know is how to read the periodic table and realize that this is highly related to how bonds are formed. Okay, so let's think about oxygen. Remember that oxygen has an atomic number of 8 at the top on the periodic table with a 15.99. Now you should know how to determine how many electrons and protons and neutrons that is, but when it comes to organic, we're really interested in bonds that are being formed. Remember that to determine what this looks like as far as bonds, we have to remember how the electron configuration is formed. So that is a 1s2, 2s2, 2p4 arrangement. What that means is that the second row has 6 electrons. Remember, it wants 8. So since it wants 8, it needs 2 more, and that's what leads oxygen to form 2 bonds, okay? And so you can look at that from a perspective of many other things as well. So I've made a chart here for you, different atoms, and the number of bonds that they form. Keep in mind, you have to have 8 electrons around most atoms when atoms are, or when compounds are formed, covalent compounds are formed. So when you look at this, you have to have the right number of lone pair as well in order to equal 8 electrons around it. So like with nitrogen, there's 3 bonds, well that's 6 electrons, which means that you've got to have 2 more electrons that are just seen as a lone pair. So see how those complement each other? With oxygen, it forms 2 bonds, so that would be 4 electrons. And then there's 2 other lone pairs, which would be another 4 electrons. And that's how this works. Now, hydrogen is an exception. To fill its first valence shell, it only needs 2 electrons, so it only forms 1 bond. Here's a translation with hydrogen. That means it has to be on the end. It can't be in the middle of things. It's going to be on the end. It's like the painting on the outside of your vehicle or something. So it's what's on the outside, okay? So we can use these general trends on a blank periodic table to sort of see what things look like without having to pull up that chart. Because when we look here, we know that hydrogen's right here. Well, so it has 1 bond and no lone pairs. But if we count over, this would be row 1. So there's 1 electron here, like all up and down here. 2 would be here. Then we skip over 3. And then we would go to 4, 5, 6, 7. And, noble gases don't really need to bond. So we're not going to deal with them very much. But when we get to carbon, we've got 4 electrons. That means that we need 4 bonds to get 4 more electrons and fulfill carbon's octet. See how this just walks over? We now go to nitrogen. We have 3 bonds with 1 lone pair. Oxygen has 2 bonds with 2 lone pair. And fluorine, or the halogens, have 1 bond with 3 lone pairs. Now, of course, you know that there are things that can be what's known as hypervalent. Once you get into very large atoms, then that's possible. But these are general rules, or general trends, I should say, that allow us to sort of start putting and piecing together molecules, because that's what organic is going to be all about. We're going to work with carbon and other things to kind of piece together these molecules. Okay, so let's look at the next little area. When we look at these structures, we need to know how to do Lewis dot structures. I know that you probably have done these before, and I hope that you have. But if you need some refresher, you need to make sure that you really get this, because we're going to do this for the rest of this, this course, as well as following courses you're probably going to have. Maybe some of you are even looking through this because you just want to learn organic, and that's awesome. But most people learn organic in 2 semesters. So, okay. When it comes to Lewis dot structures, here's how I sort of look at this. First, we start by counting the number of valence electrons for all the atoms. So we count the number from the periodic table. Valence is just that outer shell. So just how I counted, 1, 2, 3, 4, 5, 6, 7, 8, right? Add 1 electron for each negative charge. So if there's a negative charge on the molecule, you would add 1 more electron, or subtract an electron if there's a positive charge on that compound. Next, we're going to start by placing the odd man out. So this is like generally with smaller compounds. As we get to bigger stuff, we'll work on that a little bit more. Carbons are often going to form chains as we get to those bigger things, but that's okay. So I just kind of put like the different one in the middle. Usually is a good place to start. That's a general trend, again, not the only way to do things. Never put hydrogen in the middle because, as I said, he has to be on the outside. Most atoms should have 8 electrons surrounding them, and I put them, I assume, like northeast, south, and west with 2 electrons each. So that's going to represent a covalent bond. So we're going to move into like almost like thinking in 4s or 8s, depending on how you think of that. And as I said, hydrogen only bonds on the outside. So I put some examples here. If we have something like NF3, well, nitrogen has 5 valence electrons. Fluorine has 7 valence electrons, and there's 3 of them. So we have 21 electrons from fluorine. So 5 plus 21 is 26 total electrons to put that molecule together with. So I did that and showed you what this Lewis dot structure looks like here. Now, I just want to point out that if you look at the previous page that we just went through, nitrogen, it tells you, has 1 lone pair and bonds 3 times. And it shows you that halogens have 3 lone pair and bond 1 time. Well, that's exactly what we have here in the structure. So if you start to get used to one type of mentality of putting together these molecules, then the others starts to get easier, at least I hope. In another example, we can look at CO2. Carbon would have 4 valence electrons. Oxygen has 6 valence electrons, and there's 2 of them. So we would add 4 plus 12 to get to 16 total valence electrons. You put the carbon in the center. Remember, when you have electrons that are between 2 atoms, they count for both of them. So when we were just talking about on the previous page, carbon bonds 4 times and oxygen bonds twice, what that means is that we get a double bond between these guys. And so the 2 pairs of electrons that we draw between the carbons and oxygens here really represent 2 bonds. And so we still meet what was on the previous page, in that we have an oxygen with 2 bonds and 2 lone pairs on both sides of the carbon, and carbon has 4 bonds. And so that's sort of how we do it. Okay, good. Hopefully this is a good review for you. Next, we move on to formal charges. So formal charges we have to look at for individual atoms. And this is something you'll sort of get used to, because most of the time if something looks a little bit off from what is on the last page, then that's telling you, hey, something's different here. And if that little bell goes off in your mind, that's probably telling you that there is a formal charge somewhere. And that is okay. That can happen as well, especially when it affects giving something its own octet. For example, you may have an oxygen with a negative charge on it, and it would have then 3 lone pairs and 1 bond. That is a perfectly not normal thing to see. So then let's look at how to calculate that. It is the number of valence electrons from the periodic table, the same number we just counted, minus, and I put this in parentheses on purpose, this is the whole thing right here, okay? So the number of bonds and the number of lone electrons, not pairs, the number of lone electrons. So you can consider it this way. When you're looking at this, it's like the number of bonds, you count 1 electron for that bond for that atom. And then you total up the number of lone electrons it has, because it sort of doesn't share those are all for it. And then subtract that from the number of valence electrons from the periodic table, because that would be your formal charge. So if we're looking at sort of what I had mentioned, let's say that we have an oxygen with 3 lone pairs here. Well, it has 6 valence electrons. It has 1 bond. And right now, it has 6 lone electrons, which means that the formal charge on an oxygen like that would be a -1. Okay? And that's how we would do that formal charge. Okay? The formal charge of a particular atom should be the same of the formal charge in an entire molecule. So if you have a formal charge in the molecule, that's a sign that there should be something off on that, or something that is a little bit different on one of the atoms, and that's where that charge comes from. Every once in a while we have what's known as a zwitterion, which is a compound that has both a positive and a negative in the same structure, but those are relatively rare depending on what you're looking at. In biological systems, you see those a lot, though, for certain things, but we'll handle that when we get to that, okay? Okay. So now let's start looking at what type of things electronegativity affects. Remember, on the periodic table, fluorine, which is the halogen in the top right corner, is the most electronegative atom. This is going to increase through the periodic table as you move to the right and up the periodic table towards fluorine. So the closer you get to fluorine, the more electronegative, generally speaking, are the molecules. And what does this like electronegativity mean? Well, it means that you are pulling electrons towards that particular atom. But it can only pull from those atoms that don't pull back. So like, for example, if you have O2 and oxygen is connected to itself like this, there's an equal pull from each of them, which means that there's no actual like polarity in that particular molecule. One of the things that I see a lot of people struggle with, and I just want to make sure that we know now, a CH bond is not polar. A lot of people will show you there's this chart we can go by and let's figure out how to calculate polarity and this, that, and the other. And that can be more accurate. I will just tell you from my perspective, I tend to look at things and over time you start to recognize, yeah, that's going to be polar and that's probably not so much. So there's a difference. It's not just a yes, no, is there a polarity here? It's how much polarity it can exist is also something to keep in mind. So trying to give you some examples here might be a little bit more helpful. So if we just start with CH is not polar and things that are alike that are pulling opposite directions but are sort of the same, let's not worry about those, and those are considered to be nonpolar. Then we can look at some other things. So we have like CO. That CO bond, oxygen's more electronegative than carbon. And that's enough to make a polarity in that bond. And so we write that by simply putting this partial negative over the electrons, over the oxygen, and a partial positive over the carbon. You may also have seen that in a way that's drawn like this. So that's to show that the electron density is going towards the oxygen and away from the carbon. So the carbon's partially positive, the oxygen is partially negative. These are partials, not full charges. Okay. An OH bond, the oxygen's going to pull electrons towards it, so it's partially negative, and hydrogen is partially positive, or drawn in this way. And between carbon and fluorine, carbon is donating some electrons towards fluorine, so it goes that way, and there you go. Okay. Now, what I mean by it's relative, remember, fluorine is the most electronegative atom out there, so that might be more polar than a CO bond. But that may not be as polar as a C double O bond. It depends on the situation. So these are all kind of relative, and we have to keep these things in mind as we go through. Okay. Sometimes there are what's known as inductive effects of polarity. So let's say that we have carbons that are in a chain like this. Yes, we have a fluorine that has a partial negative charge to it and a carbon that has a partial positive charge to it. But even this carbon right here can be affected by that fluorine. And that's what we call inductive effects. So it's a little bit positive there as well. So this can go through a chain, and there's other things that can affect negativity as well, okay? Polar covalent bonds are not actual positive and negative. And it's what I said just a minute ago, but just pointing that out again, okay? But this is going to affect intermolecular forces and reactivity. Okay, so remember, 2 electrons is 1 bond, right? Atomic orbitals are a result of having electrons behaving as waves. So there's different types of theories, and what you've probably been exposed to the most so far is known as valence bond theory. Well, let's discuss the different types of theories. There's also something called molecular orbital theory. Molecular orbital theory approaches things from a completely different perspective. So let me go back to valence bond theory. Remember, you were told that, okay, we have 1s orbital, 3p orbitals, and 5d orbitals. And the wave functions may look like the s looks like a circle, the p goes above and below the plane, and by the way, one of those is different than the other. And then we have d orbitals that get fancy and looks like little clovers, and there's all kinds of different stuff like that. We might have a positive and negative, so maybe this is the positive and that's the negative side. We denote that just to show that they're different. It's not necessarily they're positive and negative, they're both electrons, right? It's just that they're waves, the way that they are operating are different. Some people call it spin up and spin down is another way to think of it. And so those are orbitals, those are places where we are most likely to find electrons. Well, valence bond theory is where we know from Vesper from, and I'm going to go through that a little bit more. It's probably what you've been exposed to so far, so that's where like hybridization comes from, sp3 types of hybridizations, and that gives rise to molecular shapes and things like that we've already seen. So I'm going to go through that a bit more in the next video because that's how we approach most things commonly, to mentally think of what is the shape of this molecule. But valence bond theory does not explain a lot of things. Sometimes we need to use a different approach. And so we can use something called molecular orbital theory. Now, this theory takes things from a much different perspective. It says that we've got atomic orbitals that combine to form molecular orbitals. And overlap is what actually makes the bond happen, okay? Bonding orbitals is where things actually bond. Sorry, I forgot to write out the rest of that, so I'll have to fill that out. That's what I meant to say there, okay? So here's what we say. Let's say that we have a hydrogen here, and it's got a 1s electron. And we have another hydrogen that we're going to bond with it that's also got a 1s electron. Well, what molecular orbital theory says is that we have a lower energy bonding sigma orbital. That means the ones that overlap head on. And we have an anti-bonding sigma orbital that's a higher energy type of thing. So that's why I've got the higher energy depiction over here. So we fill things from the bottom up. So we've got one electron here and one electron here, and we fill it with one electron up, one electron down. So this is filling this bonding sigma orbital. Since we fill that bonding orbital, that means that that is a stable molecule. And that's sort of how we approach the molecular things from molecular orbital theory. It gets more complex, it does, but I just want to make sure that you've seen some of that and we'll approach those things as needed. Okay, thank you very much. I will get to the next video in just a moment and hope that you are okay with this. Please let me know if additional videos are needed. I already have several, but I'm happy to make additional videos if that's helpful. Thank you very much, and I'll look forward to seeing you on the next one.